Oh, hi there. I'm Michael Fudge coming at you from this backyard batting cage. I hope this lesson helps you get into the swing of things so that you can hit this one out of the park. All right, let's get started. All right, everyone, prepare to have your mind blown as we cover transaction management and concurrency control. The agenda. What are database transactions and what are the ACID properties? How do we write code to be transaction safe? And what is concurrency control and how is it related to transactions? And then we'll look at advanced issues such as locking and deadlocks and versioning. So let's start out covering what is a transaction. Basically, a transaction is any logical unit of work in your database management system that is a combination of reading and writing. So for example, you might have code that does a read, and then based on the output of the read, it does one or more types of writes. It might do an update, or it might do two updates, or it might do an update and an insert. So the fact that you have more than one read and or write is an important aspect of a transaction. It's a form of data logic. It usually consists of several read-write operations. It can consist of just one read or one write, like it could just do an insert, but those tend to be trivial transactions to handle. The transaction should operate independently from the other units of work going on in the database. That is, they should be in isolation from one another. And that transaction should know about nothing going on other than what is happening in its own little world. This is a very important part of transactions. So let's try to explain this through a real life example where you have one person on the left here that has money and then another person on the right that has a laptop for sale. This is not a database transaction, but it does give you a good idea as to how database transactions might work, because this involves two operations: one person giving another person money and then another person getting a laptop in exchange for said money. So, hey, I'll give you $500 for that laptop computer. Okay, it's a deal. So the money, the laptop might go over to the person. At this point, the transaction is pending, right? It is not done. This is not how we would consider this finished by any means. And we wouldn't want someone else to see what's going on at this point because we're in the middle of a two-step operation. And then the second step would be we give the money to the person who had the laptop. And everyone's happy. Everybody walks away with what they wanted. And this transaction totally worked the way it should. And the transaction's complete. So one thing that transactions do in databases, unlike real life, right? Because in real life, you could get your money taken and not get your laptop, right? So database transactions guarantee no intermediary states. That is, here's the before state, and then here's the after state. And so these states would be invalid. A state where this person took the laptop and kept the money, and the other situation where the person gave the money and didn't get the laptop. These two states at the bottom are guaranteed to not happen if the transaction is designed correctly in the database. So that's important to recognize, is that, you know, in life when we have transactions, sometimes they don't go as planned, but in the database management system, the transactions will happen as designed. And we will not have states like the bottom two. Let's do a demo. And in this demo, we will set it up by explaining the need for transactions and why database transactions are important and why they need to exist, and when you might decide that they are necessary in your database. There's usually a common pattern here that shows you that they're necessary. So before we get into the demo, one thing to note is that you will need the accounts table, which is created when you create the demo database. If you don't happen to have this SQL script for the accounts table, you can always head out to the Learn Databases GitHub repository, and you'll find it under Schemas, Demo, MS SQL, Accounts. And it's just this little script here that makes a table and adds some data to it. So you'll need that. All right, I'm out here at Azure Data Studio, and I've taken the liberty of writing some code already. So let's just look at the accounts table first in the demo database, and you'll see that I've got 3 accounts. I have a checking account, a money market account, and a savings account. So we're sort of simulating what you might see in a bank. It's a very strawman example, but it's good enough to demonstrate why transactions are needed. Now, in order to move money from one account to the other, it involves 2 updates. You have to subtract the amount you want to move from one account, and then you need to add that same amount to another account. So it's a 2-step process, if you will, to move money from one account to another. So you might say, well, let's write this as this data logic as a procedure, transfer funds. And then you just give it the amount you want to transfer and a from account and a to account. Sounds cool, right? So I can do a little before and after here. Let me run this, make sure this procedure exists. Okay. And then I could do execute. Well, let's do a select first. And let's do an after. And then let's move some money. And let's transfer the amount of $500. And let's transfer that from account. Let's do savings. And let's do to account. And let's move that to the checking. All right, let's just take a look at what we have beforehand first. Okay, and then let's run all 3 of these so that we can see the before and the after. We're going to take 1,000 from savings and move it to checking, or 500 from savings to checking. So we have before the procedure runs and then after the procedure runs, and we move the money. Cool. So you might say this procedure works, and what's the problem? Why do I need transactions? And, Mike, I don't see the big deal here. Well, transactions, when it works, you don't see the need for transactions, right? It's only when you get screwed out of getting the laptop or you get your money taken away that for giving someone the laptop that you recognize that there's a problem. So you have to generate a problem in order to see that your code is not transaction safe. When your code just runs, it's going to be exactly what you want, right? So you're not going to see that it needs a transaction. So in order to show you that, let's write some bad transactions, or some bad, yeah. These are business transactions, right? So what if I tried to move more money than I had? For example, I only have, let's see what we've got now. What's our current balances? I only have $500 in the savings, right? So let's move $5,000 from savings to checking, right? This is going to violate a check constraint that was put on the balance column that says the balance cannot drop below 0. There's a check constraint there. Want to make sure that that doesn't get violated. It's right here. Right here, there's the check constraint. All right, let's run it and see what happens. Okay, so yeah, it blew up. But it didn't take the money out of the savings, but it then just added the money to checking, right? So I magically have gained $5,000, which is totally awesome, but really bad if you're a bank. Right? So, miracle, $5,000. All right, so that's problem number one. And why does this happen? Because this fails, but this succeeds. And what we need is we need to design this so that both of these, if one of these does not work, the other one does not work. I don't care if they both execute. I just want to make sure that if one of them doesn't work, the other one doesn't happen. Okay, so that's problem number one. Problem number two is, what if I specify an account that doesn't exist? All right, so let's move money. Let's do this again. I'm just going to copy it because I'm lazy. And let's say bad transactions, bad account. Right. So this is not necessarily an error, but a fact that there's no rows affected by the update. Like, for example, let's move it from the saving with a Z. Now, there is no account called savings with a Z. And therefore, because there's no account, this has no rows affected. And then, therefore, it doesn't happen. But it moves the 5,000 into checking. I could reverse this and call this savings with an S and checkings with a Z, and the same thing would happen. I would lose the money out of savings and then not have it into checking. Okay, let's just stick with the original example. Okay, and we'll run this, and then I've got another miracle $5,000 in here because it couldn't find this savings account. If I look at the messages, there's no errors. It just says 0 rows affected, 1 row affected. Okay, 3 rows affected is this. This procedure does 2 updates. The first update had no rows affected. The second update had 1 row affected. So there's 2 conditions that can cause your transaction to not work. One is you violate an integrity constraint and it throws an error. The second is the anticipated rows that should have been affected weren't affected, and therefore the whole transaction should not occur. So that outlines the needs for transactions, right? We need a transaction, and we need to write our code to be transaction safe whenever we are performing 2 or more DML statements together into one logical unit of work. So we have this procedure, transfer funds. We want it to be treated like a single logical unit of work. It really consists of 2 steps, and they need to somehow guarantee that both of these steps happens. All right, let's talk about the ACID properties of a transaction. So what does ACID mean? It's an acronym. It stands for atomic. Our transactions need to be atomic, which means they cannot be subdivided. They should be treated like they're their own statement. Like, you've got an update statement, you've got a select statement, you've got an insert statement. If you combine 6 inserts and 2 updates together, the atomicity of the transaction means that it's just a single command, and it just looks like a single command and works like a single command. And it either works or doesn't. Consistent. Transactions from one state to another should survive with their constraints intact. So if a part of a transaction violates an integrity constraint, it will be considered inconsistent and then should just not happen. Transactions are isolated. The world in which that transaction is building out its steps is self-contained and not known to other transactions. So if someone's reading the accounts table while I'm making changes to it, they would not see those pending changes to the accounts table. And transactions are durable, which means that once the transaction has finished, the changes are written to disk and they are permanent. So let's sort of explore all of these ACID properties through a couple of examples. We'll go back to using our famous accounts table, but we'll just sort of do it through slides. So let's suppose we want to transfer 1,000 from savings to checking. Before we have this, after we have that. So easy enough, right? We just move them from savings to checking. Boom. Okay. What makes this atomic is that if we transfer 1,000 from savings to checking, it's a 2-step process. Step 1 is we remove the money from savings. And then step 2, we add it to checking, right? Now, what makes it atomic is that During this step in the process, when there's no money in, when the money's out of savings but yet to be in checking, nobody else will see the data in this state, okay? Because this is an intermediary state in the transaction, and it's not available to be seen by others. So if I go to an ATM and say I would like to withdraw $1,000 or move $1,000 into my checking account, while this is happening, if my wife went to another ATM, she would see the data in its before state like this. Or she would wait and see it in its after state, which would look like this. Okay, but the other user would not see it in its intermediary state, which is this. Okay, that's what atomic means. Consistent means if we violate any integrity constraints, the data will revert back to its original state. So here's the original state. We try to move $2,000 out of savings. That leaves us with a negative balance, which causes an integrity constraint to fire, which in turn rolls back the data back to its original state like this. And therefore, that transaction doesn't occur. That's consistency. When the data, basically what consistency means is you can never save a transaction if the result of the transaction will violate an integrity constraint. So the fact that doing this transaction would violate the integrity constraint of having an account balance under zero, that can never happen, and therefore this cannot be a state that gets saved permanently. Isolation means that when the transaction occurs, somebody else doesn't get to look at what the transaction looks like in the intermediary state. So if I'm going to transfer 1,000 from savings to checking, someone has to wait while this is occurring, and they would recognize the current balance like this because the other transaction is pending. And then they would, after waiting, see this, which is what the transaction looks like when it's over with. And then they would see a balance of 500, right? And the numbers might change right underneath their nose, but what they wouldn't see is that intermediary state where there was 500 in one and 400 in the other account. Because that would be very confusing to people, right? They would say, what happened to $1,000? Okay. So what does durability mean then? Durability means that the state before has been saved to disk, and the state after has been saved to disk. And those are permanent. So there's no way to roll them back. The only way to deal with a durable transaction is to undo the transaction, move the money back from checkings into savings. And you've probably seen this if you go to a big box retailer and you buy stuff and then you check out and then you're walking to your car and you're like, whoops, I didn't mean to buy this mug. I want to return it. And you have to go to a separate line to do that. You have to undo the transaction. You cannot cancel it. Let's talk about how SQL supports transactions. Let's take the code we have here, a couple of update accounts, right? And then what if we rolled them in commands like this? This would tell SQL Server that we want to nest these two update statements into a transaction and treat them as a single logical unit of work. Now you're going to see that this guarantees that they will both occur together, but it doesn't make any guarantees to consistency. It doesn't make any guarantees to data integrity, anything like that. That's still on you to figure out, because you're blindly committing the work, whether or not one of these fails or not, and whether one of these actually takes money out from the right account. So there's a little more to it than this, but this is a start. So there are four commands that you want to learn here. Begin transaction, or begin tran, makes a starting point of a transaction. And what it does is it pretty much takes your data at that state and puts it in a temporary space for you to work from until it hits a commit, at which point it would then save it all permanently into the database, or it hits a rollback in which it like erases all of the work you did. It just says undo and cancels all of that work. There's also a variable called tran count, and the variables that begin with 2 ats are internal variables in Microsoft SQL Server, and this variable lets you know that lets you count the number of pending transactions. Let's do a demo here. Let's go back to Azure Data Studio, and we will play around with transactions and show you that nothing is permanent until you say it's permanent when you use transactions. And this is actually a pretty cool thing and pretty darn useful when you're playing around. You'll probably wish you had this in the beginning of the class when you're making all these tables and making them wrong, because you can just keep rolling them back until you know you get it right. Okay, let's play around with it. All right, I'm out here in Azure Data Studio. Let's get started with the demo. Make sure I'm in the right database. I am. And let's do a begin transaction. Let's just run that. And then I'm going to do a select tran count. And I'm just going to run this. I don't want to run begin transaction again because that's going to start another transaction. So right now I have one transaction pending. Now if I run this whole script again, now I have 2 transactions pending, right? So every time I run begin transaction, it says set aside a temporary space where you can do some work in isolation. And I don't want to have 2, so I'm going to issue a rollback. And that's going to abort one of the transactions. And now I'm back down to 0 transactions. I aborted both of them because they were nested inside each other. So let's play around with these transactions. Let's begin our transaction and then let's do something crazy. Like how about we drop table. Well, let's drop table Fudge Mart products from, I'm in demo. See that? And there's a table. Let's drop this Micazon products. Now let's delete everything from it. Let's delete from Micazon products. Then let's select everything from Micazon products. Okay. And then we're just going to roll back. I'm going to run this whole script. Okay. Oh man, look at that. I just deleted everything from that table. Or did I? Because I've rolled back the transaction, right? So if I select from Micazon products under here, the data's all there still. Because that transaction, when you say begin tran, it makes a temporary space. You delete that data in that temporary space. Then you query that data in that temporary space. Then you say throw out the temporary space. Then you go ahead and just look at the data and it's the way it was because it threw out that temporary space that you created when you generated that transaction. So anything you do in the transaction is temporary. So if I were to go here and do a create table, that would be temporary. I could go in here and do drop table accounts. I'm going to go. And then let's delete Micazon products. And then let's have another go. And then let's say like if exists, select star from sys objects where name is accounts. Let's print account exists. Accounts table exists. Let's try that. And then I will not roll it back yet. Okay. screwed this up. It goes like that, right? Let's just run this one. Okay. And then if I go over here, you know, and I do, let's do select star from information schema tables. The accounts table is gone. See that? It's not in here anymore. The mic is on products table has no data in it. Right? And if I go, this is interesting. If I go over here, right, and I say, hey, tables, let's refresh this. And let's try to select from this accounts table. I'm waiting. And I'm waiting. And I'm waiting. And I'll be waiting forever because this transaction is pending and it's in its own universe. And this new universe where I'm trying to query accounts table is waiting for this transaction to end because it's pending. So let me roll it back. And then boom, the other query runs immediately. Crazy, huh? But that's the isolationist world of a transaction. The changes that I make occur in isolation in that temporary space I build. And therefore, some other transaction that's going to start where I just, want to do a select, that has to wait until there is a release of the dependencies of that transaction. So if I run this again, right, and don't do the rollback, let me run this all again. But one thing I didn't change is contacts. Contacts wasn't affected. I have accounts, right, and information, and mic is on products, but I didn't mess around with contacts, right? So let's see, can I query that one? No, I can't. And that's because right now the database, because of what I did when I dropped a table, that's a database level activity. And so it really says until this transaction is resolved, you can't really touch any of the other tables because you dropped one. So let me roll that back because I don't want to commit any of these things. And then, boop, there we go. It works. So what about a commit? Well, a commit, just works the way it would normally work. So if I were to come down here and do begin transaction and then insert into flag colors, and I forgot what's going on with the flag colors table. I have color and country. So maybe I should select here. Let's see what we got in here. Okay, so let's do flag colors, color, country, and let's add white, and then Italy, and then let's add some more. And then we add green. And we'll also add red. Oh, I forgot the word values, didn't I? Yeah. Well. Values. And then let's do this. Let's add one more that we know is not going to work. Like red again. And it seems to be complaining about something. Oh, I forgot the S. There we go. So that's good. And now let's just commit this. So you might think, works, make my temporary space, right? Make my temporary space. That works, that works, that works, that doesn't work. So it's going to roll everything back. Well, I have to tell it to roll things back. So this is going to insert this, and not insert that. That's basically what it's going to do. It's the same as if I didn't put begin transaction and commit around it. Because I have to control when the commit happens versus when the rollback happens. It's my responsibility as the person writing this data logic to do that. So if I may, just to finish out the example, let me run this. Worked, didn't work, committed. And then if I just do a select, the Italy stuff is in there. Italy. Okay. So it's really on me to figure out, when to commit, when to roll back. I want to have something, some logic like, if there's some kind of error, roll back, else commit or something like that. I want to do something similar to that to sort of make this happen. And then we're going to learn about that coming up next. All right, so what is the recipe for writing code that's transaction safe? That is, how do you know when to roll back, right? Because we always know when to commit when things work, right? You know what? You want to roll back under two conditions. Basically, you want to roll back when some error occurs, like, something drastic, like the disk is full, or there's some physical issue with the system. You also want to roll back when you violate any sort of integrity constraint or when SQL Server or any DBMS throws an error. You definitely want to roll that back. You also want to roll back based on some data logic, like when you expect something to occur and it doesn't. So you have to sort of write your own tests. So we're going to break this transaction safe code example up into two steps. The first step is we're going to show you how to handle errors. The second step is we're going to show you how to handle custom data logic. So error handling in Microsoft SQL Server and in most SQL databases have what is called a try-catch statement. And the way try-catch works is the try says anything within this try block, if an error occurs anywhere in the try block, jump to the catch block. So this means we don't constantly have to do an if after every single statement to see if an error occurred. It's very handy because you just say, try all this. And if one of these generates an error, I don't care which one it is, jump down to this catch and roll back. So you see the pattern that I have here is it's always try, begin transaction, do a bunch of work, and then commit and then try. And so if anything within this try blows up, it will jump down to catch and then print the error and roll back. And so this is sort of a better way this definitely addresses the data integrity constraint problem. It doesn't address the custom business logic problem, as we'll see, but it does address the data integrity constraint problem. So let's do another demo and we'll show you that this is not perfect, but it's better. And we're going to write another transfer funds in Azure Data Studio. Okay, for the sake of saving some time, I just put the procedure in here. So I have my drop procedure exists, then here's my same procedure as before, transfer funds, same contract. It has, input your money, input your from account, input your to account. I just called it V2, so you would have both. And then I have begin, try, and try. And in between here, I have begin, transaction, commit. And then I have my two updates. So basically, this is going to, nest both updates in the transaction. If one of these updates throws a data integrity constraint generating an error, it will jump down to catch. And then it will print out with the select statement the error number and the error message so that we can see them on the console. And then it will print rolling back, and then it will actually do a rollback. Let's try out the procedure here. First of all, let's execute the procedure. Okay, we're done there. And let's see what we got in accounts. Got a lot of money in that checking account from the previous example. That's fine. I should have rolled it back, but I I didn't. So I guess if I want to correct things, let me just update accounts and set that checking account, set account, set the balance, right, to 1,000, where the account is checking. Let's just put it back the way it was. There we go. All right, now let's play around with this. Let's execute P transfer funds version 2. Let's transfer an amount. Let's make it work. Let's transfer an amount of 250 from the savings account and the to account is checking. And let's do a before and after. Okay, but this one works. This one works. It only works because there's enough money, right? Okay, before we had 1,000 in that checking and 500 in saving. After we have 1,250 in checking, 250 in saving. It works. Okay, now let's do one that doesn't work and see what our transaction does. So this one violates data integrity constraint. Checks constraint, to be exact. We're going to move 10,000, a cool 10 grand, from savings to checking. There's not enough money in the savings account to do that. And it says rolling back here. And the error that we got was the update statement conflicted with the check-in string. Okay. So there you have it. The error occurred. And because the error occurred, we didn't succeed in moving the money, and the before and after states are the same. Before 1250, 250, after 1250, 250. It rolled it back. Good, right? So if you don't want to print the error message, if you want to see the error message, you can just throw, I think you can throw it, the error number. Okay, we'll do that in the next example. Make it look a little better. All right, but this is not perfect because it doesn't handle our custom data logic. What if you enter in an account that doesn't exist? Like, let me mysteriously move money, still does not work. Let's move 10 grand from the savings with a Z to checking. This still doesn't work because there's no errors. It's just no rows affected. So before 1250, 250, after 11,250, 250, we look at the messages, it says committing. No rows affected on the first update, one row affected on the second update, committing. So yes, we need more to our transaction than just update. We need to check to see if the update really did the update. Okay? Or we need to check if the account name is valid. We have to do some kind of check here. Okay, so let's move on with the lesson. All right, how do we roll back from custom data logic? Okay. For example, you might have a row that updates, but no rows were affected. Or the insert, well, the insert would always throw an error. It's mainly in the update or the delete or the select statement where there's 0 rows affected, where you need to handle custom data logic. So the trick here is there is a internal variable in SQL Server called row count, And the row count variable tells you the number of rows affected from a statement. You see this a lot when you run a statement. It says 2 rows affected. If you print row count, it'll print 2, therefore telling you how many rows were affected. And you can use this to, if you expect a certain number of rows to change, to verify that those number of rows changed. You can then throw a custom error. And throwing a custom error allows you to generate your own error message that will then cause the transaction to roll back, because the catch statement will fall into the catch block because an error happened. So let's wrap it up then with a final version of the transaction that handles some custom business logic with PE transfer funds. All right, I'm out here in Azure Data Studio again, and here's my procedure. The top part is the same, except it's version 3. And now I need some variables to keep track of row counts. And then I try my transaction. I begin my transaction in the try block, and I do my update. And then I say, hey, if the row count isn't equal to 1, then, throw an error. And then I do this update. And if that row count doesn't equal a 1, I throw an error. And you'll notice that I have to give it an error number. And the error number has to be higher than 50,000. Those are reserved for user-defined errors. So it's a good idea that each of your different errors has a different number so that you can say that there's slightly different errors. This is the error on the from balance, and this is the error on the to. And then if all that works and the row counts match, I commit. Otherwise, I'll fall down here and I'll throw my error. So I'll get the red message, and then I'll also maybe print the error message out. Okay, let's give it a shot. And then, of course, most importantly is roll back. So let's run this, make sure it's there. And let's try an example now. Let's do a little before. See what we got here. And then let's do an after. And let's run our execute in between. Transfer funds version 3. Amount. Let's transfer from savings $5,000, which doesn't exist. And let's put in from account. From account, right? That's not an account. And then to account, checking. So I'm a hacker, and I'm trying to miraculously give myself $5,000, and I'm going to do that by saying transfer from this account that doesn't exist. Let's see what happens. Okay, you've got your error. Could not transfer from account. Right? Before. And I don't see an after because there's an error. Very cool. Let's switch this around. Let's transfer from checking to. You never do this as a hacker because you don't want to take $5,000 and put it, in the bit bucket. You want to pull from the bit bucket into your checking account. So you wouldn't want to do it this way. But let's see what happens. Okay. Could not transfer to account. Message 5002 error. Okay. And it got rolled back. Very cool. And that is basically how you write transaction safe code. Is you use try catch. Let me make this all fit on the screen. You use try catch. You have begin transaction and commit. And then your unit of work goes here. And somewhere along the way, you need to test whether or not your unit of work did what it expected in the event that it doesn't throw an error. So another way I could have done this is I could have verified the accounts exist. So I could have said, if, I could have had something like, if exists, select, star from accounts where name equals from account. I'd say if not exists, right? If not exists. Then we want to throw, some error. Some error. And this is account. Oh my goodness. There we go. So that would replace the row count idea here, right? I would do this before I tried the update. I'd verify the from account exists. I'd verify the to account exists. Same thing, right? You just have to know what that business logic is. It's going to be pertinent to your particular data transaction, your data logic, and then you'll have to write the transaction accordingly. Okay, cool. Okay, now that we have a good understanding of transactions, let's go back to triggers again and talk about doing a prevent update trigger. Now, why did I wait until now to talk about prevent update? You can certainly write prevent update triggers without knowing anything about transactions. However, if your prevent update trigger is nested within a transaction, you want to guarantee that the rollback occurs. So usually what I will do in my prevent update is put a rollback in it. So just a reminder of how triggers work is, create trigger on table, and then normally we have an after, but now we're using instead of. And instead of will be used in a demo to show us how to not transfer money when the account is locked. So there's a column in the accounts table called locked. What I want to do is check for lock, and when the account is locked, I do not want to permit data to be transferred from that account or to that account because it is locked. So let's show you how that works with a prevent update trigger. Let's do that demo now. All right, I'm out here in Azure Data Studio again, and I have written my trigger, drop trigger, create trigger on accounts instead of update as, and then let's see if the inserted table in the trigger has locked set to 1, then I need to roll back. Otherwise, I can just perform the update as usual. Okay, that's basically the gist of the trigger. Now, one thing I want you to know, and this is absolutely maddening, I spent quite a long time on this. As you can see, I'm getting an error right here, incorrect syntax, and I have begin and then roll back and throw, and I tried to, move the throw first and then do a roll back. And it just, whatever I do didn't work. And what I found out is that I have to put a semicolon in front of throw. This is just a weird SQL parsing thing where this begin and this throw, like they need some kind of delimiter. So, it's okay when you have like if and then throw, that works. But whenever you just have throw in a block, it needs to have the semicolon in it. I don't know why. I just know it needs to be there. I had to look on Stack Overflow. So anyway, there's my trigger. I've got it written. Let's run it and make sure that it's there. Okay, and let's try our trigger out. Let's do something really simple. So nothing is locked right now in here. So let's lock that money market account. So much. I type so much better when I don't talk when I type. Okay. All right, and let's see what we got here. Whoop! I did something wrong. Because it says I can't update it because the account is already locked. Let me see what I goofed up here. All right. I don't know if I goofed up or not. Maybe I just didn't run the right thing. Okay, so now it's locked. I don't know what I did there. All right, so I have this account, it's locked. So let me withdraw some money from the money market. Let's do this. Let's update that money market. Set balance equals balance. Let's withdraw $500 from the money market. Give that a whirl. Whoa, that worked. Okay, so I must have messed up something in my trigger here. That's funky. Let me just check something here. Well, I figured out what the problem was. I never ran the trigger. That would be a problem, right? You got to run that trigger or else it's not going to work. All right, so I ran the trigger. Now it doesn't take money out of the money market. Won't let me. And if you look, and it also works with the procedure, by the way. Let's try to transfer money into the money market. Let's do this. Let's say execute P transfer funds 3. And let's transfer, and I'm just going to put the arguments in here, amount. Let's transfer $10,000 from the savings, or from the checking. And the to account is money market. See? No changes permitted to account is locked. Okay, so there you have it. It won't let you do it. That's a prevent update trigger. I like to, as a pattern in my prevent update trigger, include a rollback. You can argue that this isn't necessary, but I like to do it this way to ensure that any pending transaction that might have induced this custom check constraint from failing, because that's pretty much what an instead of trigger is. It's like your user-defined check constraint. I want to ensure that the transaction that started is aborted. So that's just how I like to do it, and that's why I waited till now to show it to you. Okay, let's go back to the lesson. All right, let's talk concurrency control. So concurrency control deals with the fact that multiple users are trying to access the same data at the same time, and that interference can cause data loss. The solution to this is concurrency control. Okay, concurrency control helps keep the data in the database transactions isolated, and concurrency control is part of every DBMS. So let's look at the concurrency question. So this person is trying to read the freshman out of the database. This person is trying to update 2 freshmen in the database. So what do we see as output? Does the person at the top see Robin Buck, which is the way it was beforehand? Robin Buck, like this one goes, and then their query goes, and then, you know, Bucky happens after, or both of these go, and then that one goes. You know, what is the sequencing here? Well, the answer is it's going to depend, because each of these statements gets queued by the DBMS, and they actually execute non-concurrently but linearly to guarantee some form of preservation over the asset properties. And so how they get ordered is going to depend. It could be ordered, this happens first, that happens second, that happens third. And this is yet another reason why we want to write transaction safe code, because you might want to guarantee that these 2 updates occur as one logical unit, and that no person in between will see an intermediary state. Now, I don't think it necessarily applies to this particular case, but it could apply. It definitely applies when you're moving money from one account to another. So how do DBMSs deal with concurrency control? Well, what is life like when they don't have concurrency control, I guess, is the first thing we want to look at. Let's think about this. We have a problem called lost update, and lost update occurs when one update overwrites another. So if we didn't have concurrency control, what can happen is something like this. You go to the ATM and read that you have $500 in there. And meanwhile, your partner goes to the ATM and a different ATM, and they read that there's $500. And they beat you to the punch and withdraw $300. And then a balance is written of $200. And you're sitting there thinking, how much money should I take out? So you take out 100 and then write a balance of 400. So the balance should be 100 because you took out 200, or you took out 300 and 100. But now the balance is 400 because it overwrote this other balance. It's called a lost update problem. And this is what happens when you don't isolate your transactions. Okay, if you do not isolate your transactions, you'll get the lost update problem. A more common problem when you don't isolate your transactions is what we call a dirty read. And a dirty read occurs when you read uncommitted data. So let's do another example. So we read the city Utica, and then we update that city to be Rome. And then somebody else comes in and reads the city, and they're like, oh, it's Rome. And then we roll back. And it should be Utica, but this person is now using it and assuming it's Rome. Because this was temporary, it never got committed, and therefore it was in that little workspace, and nobody else should have been violating that workspace. And as a result, this person is now using dirty data. And this is a big problem, and something that we can demonstrate in the DBMS, and will. Continuing on the concurrency control journey, let's look at locking and serializability. So how do DBMSs maintain concurrency control? Basically, they use two approaches. They use serializability, which is they finish one transaction before starting another. This was demonstrated before with the ordering of the updates and select statements when people were reading from the students table in TinyU. And then comes locking mechanisms, and locking mechanisms control who waits for the data, basically. So this is a demonstration of a locking mechanism. So let's go back and do that ATM example again. So I request access to my account, so my account gets locked. Then I read a balance of 500. Then my wife goes to another ATM and she requests access to the account, and she sees a sign that says, please wait. Then I do my business and withdraw $100, and then it writes a balance of $400, and the transaction is committed. I was in temporary space, transaction's committed, the lock gets released. And we saw that demonstration where I went to go query another table and it just said, wait, dude. And then as soon as I rolled back that transaction, the table showed up. Okay. So then on the other side, transaction B will acquire the lock once the other lock is released, and then I can now read the proper balance of 400. There are different locking mechanisms. There is different granularity of locking. You can lock at the database level, table level, the page level or block level, the field and record levels as well. Generally, most DBMSs will figure out the right granularity based on the problem you're trying to solve. If you're, for example, dropping a table out of a database, it has no choice but to lock the entire database. Okay? If you are manipulating the table itself, it can generally just lock the table, other than dropping the table. But if you alter the table, it's fine. If you are updating rows, it will generally lock at the page level or block level. Okay, and the page level is a set of adjacent records. stored in the DBMS table. There are two kinds of locks. There's a shared lock, which permits the ability to read but not update. And then there's an exclusive lock, which does not permit anyone but one person to do the update. So let's talk isolation levels. There's an isolation level called versioning, which maintains multiple versions of the data to be modified as part of the transaction. It doesn't allow concurrent writes, but it will allow concurrent reads under this scenario. And then attempts are allowed, but subsequent writes are rolled back and restarted if you make an attempt to write. So here's an example of versioning. It's like a more graceful form of locking that lets multiple users read, but then as soon as somebody starts to write, you wait until there's a commit. And if you try to commit while somebody else is still pending a transaction, you get rolled back because the first person that asked for the transaction has the lock. So in a versioning, what would happen is it would do this, and then it would try to do this, and it would roll it back. Then this would commit. Then it would restart this and commit. So it doesn't give you an error. It just retries. So you might see, that ATM metaphor, you're waiting a little longer for your money to come out, as an example. These are all just kind of like, the reason you wait with an ATM is not because of this, but I'm trying to just draw that same kind of analogy for you. So there are various isolation levels in a database for your locks. There's read uncommitted, which says, I don't want to lock at all, right? So you can easily see the dirty read happen when you do read uncommitted. There's read committed, which is the default, and that just picks the right opportunistic lock based on whatever you're doing. Are you altering the database? Are you dropping a table, altering the database? Or are you just manipulating rows within a table? Then there's a serializable lock, which is a form of read committed lock, but it's a little stronger. What it does is it says, hey, I noticed that you are using the customers, the order. I noticed that you're manipulating an order. So I will go look at the foreign keys in orders, and I see, oh, here's a customer. So I'm going to lock that row in customers as well. So it's a way to sort of lock related data, pre-lock related data to avoid potential changes to dependent data. And then there's the read committed snapshot, which uses versioning. So it's just like read committed, only instead of using locking, it does versioning instead. So it just keeps doing transaction retries. Let's do a little walkthrough of concurrency control here. And what we'll do is we'll just demonstrate what a dirty read looks like. We'll demonstrate what a lock looks like. And we'll demonstrate the danger of a dirty read and why you do not want to do read level uncommitted. So one other thing that I do want to talk about when it comes to locking and stuff, when you have a performance issue in your database, the wrong way to go about fixing it is to turn off locking. Okay, that is the absolutely worst thing you can do. Yes, the queries are going to work, but the data is not going to be right, and this is definitely not something that you want to do. Okay, so let's go and do this. All right, we're out here in Azure Data Studio, and we're ready to do our demo. So I've written some code for you already. This is going to change the savings account to a balance of 9999. Okay, and let's just start an outstanding transaction. And the only reason we're kicking off a transaction and not committing it is so that I can simulate concurrency. If I don't do this, I can't simulate concurrency because the DBMS is too fast for an old guy like me. So let's just run this. Okay, now we got an outstanding transaction, and we updated that balance. Now let's open up another window and pretend to be another user. Okay, and in this user, let's just, and I'm just going to copy and paste this so you don't have to watch me type. Let's set the transaction isolation level to read committed, which does the most aggressive form of locking, which is the default, by the way. But I just want to make sure, because I've done the demo a few times, that I have the right lock level set. And then what I'm going to do is I'm going to read from the database where, let's just read the checking account. Okay. Now, we're waiting. We're waiting. We're waiting. Okay, let me go back here. Let me roll back. All right, I got it working. See, I can read. This is the way it should work. Okay, I should be able to run this. And then if I look at the transaction count, 1, I come over here, run this, waiting, complete the transaction by rolling it back, and then immediately over here, oh, see, now it's not working again. I think there's some weird thing going on with Azure Data Studio, because this is not the normal behavior that it should have. All right, to confirm that I am not completely out of my mind, I switched from Azure Data Studio to Microsoft SQL Server Management Studio, which is like the old client, and this actually behaves properly. So there must be a bug in the way that the Azure Data Studio works. So if I may just really quickly show you again, if I run this, right, and I have a pending transaction now, and then I come over here and I run this select statement, I should be able to see the output, because I am locking this row, right? If I change this to savings, oops, this will not give me output because I have a lock currently on this row because I'm updating it, right? I'm updating that row. So if I roll this back here, then boom, instantly I see the output over here. Okay, so that is an example of isolation level read committed, which is the default. Now, if I change that to read uncommitted and run this, that lets me read the data even in its intermediary state. So this is a very dangerous thing. So I'm going to run this again over here. And so now I'm pending a transaction, right? I'm pending a transaction. And I can read the savings account and see that the balance is 99999, which is not right because I have not committed this transaction. So it says 9999. I read it, and then I can roll. This is called a dirty read. If I roll this back, right, and then run this again, I have the actual balance of 250. So this is why read uncommitted is dangerous, and why you don't want to use your database in that manner. So another thing aside of read committed and uncommitted is there's a property that you can put on the from clause called no lock, like that. Let me see if this works. Okay. Now, watch this. It says read committed. Right? I ran that. Okay, so I'm back in read committed mode. Then I'm going to run this. And then I'm going to run this. Okay. Now it says no lock. Okay, but it's gracefully requesting that I don't put a lock on here. Okay, but this has already put a lock on here. Right, so that's still good because even though I have globally set it to read committed, right, which says make sure you have locking, if I request the table with no lock, I still don't see it. That's good. So let me roll this back. So what does no lock do? No lock means when I run this select statement, I don't incur a lock on it. Which you might say, well, that seems really good because then I don't have to worry about the read operation getting in the way. But you still have to worry about potential dirty reads under this scenario when you're asking to query a table without locks. Okay, so you have to be careful of that. Let's talk about our last topic of the day, deadlocks. A deadlock is a situation that occurs where two transactions compete for locks and refuse to give up each other's locks. Okay. So there's a situation, generally it always occurs the same way where, transaction A starts by locking table 1, and then transaction B starts by locking table 2, and then later on transaction A locks table 2, requests table 2, but there's a lock, so it waits, and then transaction B requests table 1, and there's a lock. So row level locks can help, but this is still a possibility. The idea is to set a lock timeout here so that you're not waiting forever for the deadlock to finish. Okay, the default deadlock timeout is -1, never. So here's an example of a deadlock. Transaction A goes to update user 1. Transaction B goes to update blog ID 7. Along the way, transaction A needs something from the blog. It needs to read from the blog, for example. Okay, so it's waiting because this guy's doing an update. And then likewise, before this guy can do an update, maybe it has to do some kind of reader update on users. So now they're both waiting for each other and they just go, I don't know what to do. Okay. Let's give a demo of a deadlock. And one of the nice things about the newer versions of SQL Server is that they detect deadlocks rather quickly and don't have you waiting forever for the deadlock. It detects the condition immediately and then throws an error. Whereas in the older ones, this was rather dangerous. You could literally sit for 60 seconds before you figured out there's a deadlock, and this caused major performance issues. Okay, hopefully this demo will work unlike the last one. All right. Okay, I'm out here in Azure Data Studio, and I've got this demo set up for you. And basically what I'm going to do is start a transaction and update a student. Then wait 5 seconds and update a major. Why am I waiting 5 seconds? Because I'm slow and old, and I need that time in order to run this one and then run that one. And then concurrently, I will be updating the accounting major and then waiting 5 seconds and trying to update the student. And you will see that this will incur a deadlock because this one is going to put a lock on that student row. And then later on, this one's going to request that student row, but it's going to be locked. Meanwhile, afterwards, this one's going to request a lock on the accounting row, and that row is going to be locked here. So let's give the demo a shot. Run it, run it. Oh, I'm sorry, I highlighted the whole thing. Let me try that again. Boom. Okay. There you go. So we hit a deadlock scenario and this error message occurred over here. Now that was a little bit of waiting, but not nearly as much waiting that has been done in the past. I love this error message. The deadlock victim, right? Transaction process was deadlocked, resources with another process, and has been chosen as the deadlock victim. Rerun the transaction. What's nice about the newer versions of the DBMS is they will punt much more quickly. They will give up a lot more quickly when they reach a deadlock scenario. In the older versions, boy, you could wait a very long time before you reached a a deadlock scenario and got a report back that it happened. And you can see that there's a lot of just waiting while it figures out what happens. Okay. Woo, lot we covered there. Let's sum it up. So transactions are multiple statements that are treated as a single unit of work in SQL. They have the ACID properties of atomic, consistent, isolated, and durable. To make your code transaction safe, you must roll back on error and or roll back when the expected data does not match the results or the data that comes in to your data logic is not what you need or want. So some of the data logic you have to test yourself for rollback. Others you should just blanketly roll back on error. So both conditions are needed to make your code truly transaction safe. Concurrency control governs how the transactions are managed within the DVS, and basically what we're looking at here is they are executed in a serial order and locks occur on the resources that are being manipulated. A deadlock scenario can occur when two or more transactions are waiting to give up locks, and the good news is the database will recover from this. The bad news is it does take a little bit of time for the database to recover from a situation like this.